Welcome back. Let's continue on chapter 5, section 4. It's application of the integrals that we've learned. Let's first introduce some of the notations, some of the physics background. Newton's second law of motion, and through that we discuss what is work. Okay, so work is defined to be force multiplied by the distance. W equals F times D, where F is the force, D is the distance. This is called linear distance. And force could be calculated through Newton's law by M times A. M is the mass, A is the acceleration. A is basically the second derivative of the position function with respect to time. If you take a derivative twice with respect to the time of the position function. So if the position function st is given, you can find the acceleration function by taking two derivatives. First derivative gives you the velocity function. So s prime t basically is the velocity, and the double prime is the acceleration. And we're going to apply these to some examples. So here, let's look at the first example. How much work is done when a hoist lifts 200 kilogram rock to height of 3 meters. Okay, so what do we know? We know M is given, is 200, and height, H, or you can call it D if you want, 3. So what we do is picking up a rock to a height of 3 meters. So this distance, D is basically the height. So H and D in this case are the same thing. So what do we need to figure out? We're looking for the work. So what is work? Work is F times D. But we don't know what is force. We can figure out the force. Force is M times A. What is A? A here is the acceleration that created through gravity. G equals to A. So the gravity, I think you should know this one, 9.8. Gravitational acceleration is 9.8 approximately. So what we can find is force. First, let's find force. So what is force? F would equal M200 times 9.8. And calculate this is 98 times 20, 0, 6, 18, 19. And W, what is W? W is F times D. So we have force, 1960, multiplied by the distance, H3. And if you multiply these, what you get is 3 times 6, 8, 3 times 9, 27, 8, 5. So we found the work done by lifting up 200 kilograms of a rock to a height of 3 meters. Okay, very simple. The only thing that you should notice that the acceleration is not given, which is basically due to gravity. Here's another one. We can kind of extend this idea from moving. Let's say if you move something with the mass m through some distance, d, from location A to location B. Distance given from location A to location B. What we can basically calculate is the force is m times A, therefore the work could be m times A times the distance. But sometimes the force is basically the function force is not a constant. In this case, our function force was a constant value because the acceleration was fixed. Sometimes the acceleration is not a fixed value. So, for example, I can give you, let's say if you go up the hill and you start the acceleration reduces. So at the beginning, let's say you go, your acceleration is higher, and if you go closer to the top, your acceleration decreases. Therefore, the acceleration would not be a fixed value. So therefore, the force would not be a fixed value. So what they can give you is, sometimes they give you a function of f and say this is the force function based on the location x. So where x is at this position between A to B. So when you're moving something from location A to B, due to the forces may be different at different locations. So what we need to do is add all these forces, because basically what you're doing when you say the work is F times D, you say this force has been done D times from distance A to distance B. So you've added up all those forces. So you can generally calculate this force by saying, let's add up all those forces from the location A to location B. And what that means is basically, let's integrate from the location A to location B of the force function. Dx is basically in smaller portion. You break it up into smaller portion. The same idea of the integral. So this idea of the force could be generally extended to calculate the work for a non-constant force. So if the force is not constant, if it's a function of x, then you can calculate the force, and you can calculate the work by integrating from location A to location B. So let's see it in example. Let's say a particle is located at a distance x feet from an origin. So let's say this is origin. There's a particle at location x, and a force F of x plus 2x, so the force function f of x is given x squared plus 2x, acts on that particle at different location. So here's what you notice is, at different location you'll have different forces. Maybe at location 1, notice 0, the force, if you calculate f of 0, will give you force of 0. At the 1, force of 1 would be replace 1 into the function, you'll get 3. So you see different forces at different locations. And we want to see how much work is done if you move this from location 1 to 3. So from 1 to 3, if x changes from 1 to 3, what is the amount of work that has been done throughout this movement? And what you can calculate is through this integral from 1 to 3 of the force function. Basically from 1 to 3, x squared plus 2x dx. And at this point on, it's just integration. Antiderivative is x cubed over 3 plus 2 times x squared over 2. You can cancel out these. Evaluate it from 1 to 3. If you replace 3 into the function, what you get is 3 cubed over 3 plus 3 squared. You replace 1 into the function, minus 1 cubed over 3 plus 1 squared. And if we add up all these, you get is, this is 18 minus 1, 17. 17 minus 1/3. So 16 and 2/3. This is the force that have been done from moving this particle from location 1 to 3. It's not difficult as long as you set up the integral properly. There is another cases that we use integral for, or we use this idea is for springs. Let's say if you have a spring that at the rest position, it's at location 0. So this 0 basically says if you leave the spring without stretching it or shrinking the spring, it's at location 0. If you stretch it to location x, so you stretch this to location x, or you can go the other way and say shrink it to negative x. The force have been done by doing this is basically a constant times x. This is Hooke's law for the spring. So the force is basically K times X. What is K? K is the spring constant. It's a constant value. Sometimes you have to figure out what is that constant. Sometimes it's given. So let's, and then you can calculate. If you find the force, you can find the work. So here's an example. A force of 40 Newton is required to hold a spring that has been stretched from its natural length of 10 centimeter to the length of 15 centimeter. So here, let me draw a picture. Let's say this is the natural position at 0. In this case, it's say 10 centimeter is the length of the spring originally. And if you stretch it to 15 centimeter, so this is kind of spring as originally is closer. And then when we stretch it, kind of spring opens up. Okay. So from 10, it's been stretched to 15. And what did I say is the force for this stretch, f of x, which is kx, is basically given when I keep the parentheses and say this is 40. F of what is 40? That's the question. Since the change in x in this case is 5, so basically we know x is 5. Distance that the length of this spring has been stretched. So f of 5 is given 40. And they ask you how much work is done if you stretch the spring from 15 to 18. You want to figure out that. So what do you need to first figure out is this constant k. How do you figure out? Through this given information. Because f of 5 is given 40. This length was 5. We can figure out the force, the constant k. So what you can say is 40 must equal to kx. But what is x? X was 5. So 40 must equal k times 5. Oh, one thing that I should tell you, I forgot to mention. For Newton, if the unit is given Newton, you always need to change this unit centimeter to meter. So instead of 5, actually you should use 0.005. So I'm going to do that. F of, not 5, but f of 0.05 divided by 100 is given 40. These lengths are in centimeter. 10 centimeter is the same as 0.1 meter, and 5 centimeter is the same as 0.05 meter. Okay, so k times 0.05. What is k? K could be calculated. 40 divided by 40 divided by 0.05. You can figure out that is 800. I believe so. 8 times, yes, 800. So we figure out k. So I can say the function f of x is basically 800 times x. Now that we have the function, we can say, let's integrate. Since we want to find the work, let's integrate from where to where. I want to find out what is the work done from 15 centimeter to 18. From here to 18. So from 15 centimeter, remember, 15 is here. The distance originally from the origin is 5. So this 15 basically represents 5, not 15, because you should assume this is 0 and 15 is 5 away. So it starts from 5 going up to 8. It's supposed to be from 10 to 15, then 15 to 18. But if we assume the natural position at 0, then going to 15 would be going to 5, and from 15 to 18 would be from 5 to 8. And again, since these are in centimeter, you should change it to meter. So from 0.05 to 0.08. of what? Of the f of x dx. So work done from 0.05 to 0.08 of kx, which is 800 x dx. This setup is kind of very important to figure out. Make sure that you're using meter and kilogram, unless they tell you something else. If it's in gram, you change it to kilogram. If it's in centimeter, you change it to meter. Okay, so here 5.0, sorry, we already have the integral. You can find the antiderivative right here. This equals to antiderivative of 800x would be 800x squared over 2, evaluated from 0.05 to 0.08, which could be simplified to 400x squared from 0.05 to 0.08. And if you replace these number and simplify, you can figure out basically what the value is here. Replace it. Let me do that too. 400 times 0.08 squared minus 400 times 0.05 squared. Try to calculate this and figure out what is that number. So this would be the work done for moving, stretching this spring from 15 centimeter to 18 centimeter. And the result should be in Newton. Whatever you get here, that should be in Newton, the unit. Okay, here's another example. A tank has the shape of an inverted circular cone with a height of 10 meters and a base radius of 4 meters. It's filled with water of the height 8 meters. So first, here, let's look at the picture. I already drew the picture. So what is given is this radius of the cone is given 4, and the height of the cone is given 10. Okay, what is the height? And they say it's filled with water up to the height of 8 meters. So if you fill it with the water will stop at 8 meters. So this height, this leftover height is 2 meters, and the water is filled up to this level. You can assume there is a circular cone and the water is filled up to this level. Okay, so this height basically 8 meters. I'm not gonna write it because it's gonna be more and more values on that. It'd be kind of counterproductive. So let me highlight this. These are the given information. Okay. Find the work required to empty the tank by pumping all the water from the top of the tank. The density of the water is given 1000 kilogram per meter cube. Okay, so there is no change of unit required. Everything is in meter and kilogram, so no change in units. Okay. One thing you should notice, we don't have the mass, because if you want to find the work, you need to find out the force. Force is m times, in this case, A, which is based due to gravity, so G. And what would be the mass? Mass is not given. What is given is the density of the water. So if the density of the water is given, you can figure out the mass by saying mass is equal to density times volume. So if you have, let's say if you have this box filled with water, so this is filled with water. If you find the volume of this box and multiply it by the density of the water, what you get is basically the mass. But in this case, what we have is, if you pick any slice of the water, if you pick any of these cones, so let's say if I pick a section of this cone, let's focus on the section. What it looks like is like a disc. Let me draw that disc out here. The area on top multiplied by the height will give you the volume of this disc. The thickness is what we call it the dx, the change in x, because x is basically the height. Where is the water? It's at this location, so we want to change it. We want to pull the water out, so from x changing from 2 to 10. 10, here's 2. Right, so if you pull the water all the way up to the top, what you need is start from 8 and go up 2 units, from 5 maybe go up 5 units, and so on. So from x, what you need to do is move this up 10 minus x unit. That's what you need to do for the water. Okay, so if you pick one of these discs, the height of the disc could be, say, the thickness of the disc is delta x or dx. The radius, we don't know the radius, so let me call it r. If you pick the radius here, you don't know that radius. And let me pick x to be here somewhere. Let that to be x. And if we figure out the radius, then we can find out the volume, because the volume would be the surface area multiplied by the height. What is the surface area? It's the area of a circle, pi times r squared. What is the height? Height is dx, or delta x. So I need to figure out the volume, then multiply it by the density to figure out what is the mass. So how do I find the radius? Okay, so let's look at the triangle. We pick triangle. What you notice is this would be the radius. This is a fixed value 4. This large length is the value of 10. And here, that height is, we pick x to be at this location, this height would be, we pick x to be from the top, then the left of this, whatever left, is 10 minus x. So I can say this is 10 minus x. Okay, so what would be the relation between radius and x? You have two triangles. One is this small triangle and the other one is the large triangle, 10 minus x and r. So what I can say is, by triangle similarities, I can say 4 divided by 10 must be the same as radius divided by 10 minus x. This is very common. We have already used this idea. This is the relation between two similar triangles. The ratio of the sides are equal. And therefore I can find out what is r. R would be multiply 10 minus x to the other side. So it would be 4 times 10 minus x divided by 10. By the way, you can simplify it. 4 and 10 will simplify. Will give you 2 and 5. Okay, so we figure out what is r. So I can find the volume. What would be the volume? The volume would be, go back to red, pi, instead of r, I'll replace 2 over 5, 10 minus x. This is r squared, so this whole thing squared, multiplied by dx. This is the volume. So how do you find the mass? Mass would be volume multiplied by the density. But density is already given. Density is given 1000 kilogram. So I can find the density. Density would be 1000 times pi times, mass would be given by this 10 minus x squared dx. There we go. So we found the mass. And what is the force? Therefore, the force would be done by moving this, multiply by the gravity. Multiply m by m times gravity, g. Right, so it should be 9.8, since g is 9.8, multiplied by 1000 times pi times 2 over 5, 10 minus x squared dx multiplied by 9.8. This is the force. We found the force, and you notice the function of x, and it already has the dx, because this dx is basically the thickness of the water. What we need to do is to figure out the work, is that you need to move this all the way to the top. So x starts, this is the location that x starts. X starts from 2 and goes all the way to 10. This is where the water level is, from 2 to 10, because the height of the water was 8 meters. So what we need to do is now figure out what is W, which would be the work, starting from 2 to 10 of the force function. 1000. By the way, I can multiply these numbers and simplify. I can multiply 9.8 by 1000, multiply by pi. I can write this as 9800 pi times 2/5 10 minus x squared. Sorry, the square is outside. Dx. Try to simplify it a bit. It's too many numbers. I'm gonna write from 2 to 10. You can square this, and what you get is 9800 pi multiplied by 4/25 10 minus x squared dx. And you can calculate this number. That is from 2 to 10. This would be 98 times 16 times pi. 98 times 16 times pi. And multiply by 10 minus x squared dx. Okay, if you multiply these, you'll get the same as 98 times 16 times pi. Just simplify it a bit. Okay, this constant, keep it outside the integral. It doesn't affect anything. It equals to 98 times 16 times pi. If you have a calculator, you should multiply this, but I don't have a calculator available. I'm gonna just keep it there, and at the end multiply the result. 10 minus x squared, you can square that as well. Be 100 minus, actually let me put them in order, x squared minus 2x plus minus 20x plus 100 dx. And integrate. Now you can integrate without needing of substitution. If you take the integral from here, to do substitution and call 10 minus x u. So what we have is 98 times 16 times pi multiplied by the antiderivative would be x cubed over 3 minus 20 x squared over 2 plus 100x evaluated from 2 to 10. You can replace 10 and 2, whatever you get, that would be the result of the work done. And you can multiply this number at the end. 98 times 16 times pi. Okay, there might have been a shorter way to calculate this number with substitution. You wouldn't need to open this 10 minus x squared. You would have to use substitution. If you would use substitution and call this u, this integral would be simpler. This constant would be still there. What you would get is 98 times 16 times pi multiplied by the integral of u squared times dx, and du would change to negative du. And the integral would be, instead of from 2 to 10, it should be from 0 to 8. Because 10 minus, it would be from 0 here and 8. Which basically cancels out the negative. So what you would get is, let me simplify this, I can answer this question now. 98 times 16 times pi times u cube over 3. So 688 cube over 3. This would be the result of all those calculations. If you calculate this, at the end, what you get is this number. Try to double check, but I expect the same result. This is, it's kind of messy, but most of the questions are very similar to these. You set up the force function, then you integrate the force function. And if it's a spring, you need to figure out that constant k. Sometimes it's given, sometimes it's not given. Find the force function. So it's all based on this force function and the integration of it. Okay, this would be for this section, 5.4 application. Next time we'll talk about the intermediate value theorem for integrals. So I'm going to stop at this point.